Section number 5 is entitled Alternating Series. Alternating series. Remember, if you have the summation of negative 1 to the n, and then goes from 1 to infinity, or even 0 to infinity. So first you get negative 1 to the 0, plus negative 1 to the 1, plus negative 1 squared, plus negative 1 cubed, and so on. Then negative 1 to the 0. Negative 1 to an even power is 1. And negative 1 to an odd power is negative 1. Adding negative 1 is the same as taking away 1. Negative 1 squared is 1, so plus 1. Negative 1 cubed is negative 1. Adding a negative 1 is the same as taking away 1. And the signs just keep alternating. Likewise, if we have negative 1 to either the n plus 1 or n minus 1, either one of them. Please don't think we have two powers. I'll talk about one at a time. N goes from 0 to positive infinity. First n is 0. 0 minus 1 is negative 1, which is odd. 0 plus 1 is 1, which is odd. You'll have negative 1 to the odd power. Plus, now n is 1. 1 minus 1 is even. 1 minus 1 is 0, which is even. 1 plus 1 is 2, which is even. The signs are going to keep, the powers are going to alternate between odd and even. Plus negative 1 to the even, etc. Negative 1 to the odd is negative 1, plus negative 1 to an even power is 1, plus negative 1 to the odd is negative 1. Adding a negative 1 is the same as taking away 1. Convince yourself of that. So again, the signs alternate forever and ever. Well, what if you have instead the summation as n goes to 0 to infinity, negative 1 to the n times a sub n. So it's the answer to this times a n. So when n is 0, you get negative 1 to the 0, which is 1, times a n, or just, I meant to say a0 actually, a0. Sometimes you can start at 0, sometimes you start at 1, it doesn't really matter. And then negative 1 to the 1 is negative 1. So you get negative 1 times a1. A sub 1. And then this is 0, 1. Now n is 2, so the negative 1 to the 2 is plus 1 times a2. What happens is the signs alternate. Assume that the a sub n's are all greater than or equal to 0. But then we're multiplying it by 1 and negative 1 and 1 and negative 1, etc. Multiplying by 1 doesn't do anything. Multiplying by negative 1 changes the sign. So this down here is called an alternating series. We're assuming that their a sub n's are all positive. It's an alternating series. And if in the bottom one you stuck in an a sub n, well then it would just start off negative. A sub 0. It would just start off negative. Plus a sub 3 minus a sub 4. It's alternating. Well, one question one might ask is, oh, okay, alternating series, cool. When do they converge? When do they diverge? Because that is what we've been talking about. Okay, so we have an alternating series test. Well, I assume it starts off with the a sub n's are greater than or equal to 0 if that then the summation, and then goes from 0 to infinity of -1 to the n, a sub n, the summation, and then goes from 0 to infinity of -1 to the n plus 1, a sub n. They converge provided that the following two conditions are met. And the two conditions are the terms are getting smaller. When it comes to a sub n and a sub n plus 1, like a7, a8, 7 plus 1 is 8. If n is 7, that's why I call this a sub 7. And if n is 7, that's 8. The next term, if n is 50, a sub 50, a sub 51. The one on the left is always the next term. If it's smaller than the term before, smaller than or equal to. And this is true for all n. That is, the terms are always decreasing. The terms are always decreasing. Now, I know most books are going to write for all n. It's really for all n large enough. We'll talk about that in a moment. The next thing is that at the end, at infinity, a sub n's must be approaching 0. Now, suppose there was a sequence where from a100, a101, a plus 102, and so on. Suppose that the limit of these terms, maybe I really shouldn't even be writing plus. Maybe I shouldn't even be writing plus. Let's just talk about these terms. Suppose that this one is smaller than that, which is smaller than that, which is smaller than that, and so on. That is, condition 1 has been met. And suppose that the limit is going to 0. That is, they keep getting closer and closer to 0. And suppose the first 100 don't live up to that. A1, A2, up to A99. Well, this here is a finite number of terms. You can add them up, and you'll definitely get a finite number. You can't get infinity. You can't add up 99 numbers and not get an exact amount. So, this is some amount. Call it k. And then you add the sum of these. The sum of these 99. They add up to k. Well, from 100 to infinity. You know, you can imagine a different sequence where the first 99s were 0. You say, but this isn't working. You can't use that rule because you don't have all the terms. All right, let's change it. Let's add zeros. So now I have the first 100 terms. They're all zeros. And I have the terms after them. Criteria 1 has been met. And I said that criteria 1 has been met because I'm telling you that A100 is bigger than A101, which is bigger than A02, bigger than or equal to, etc. And I'm saying that it does go to 0. So this is going to converge. Maybe it converges to L. K plus L converges. You add two concrete numbers, 7 and 50. You're not going to get, I don't know, or which means it diverges, or you're not going to say, oh, that's infinity. Okay, so it doesn't really have to be for all n. It has to be for all n above a certain number, above 100, 100 and above. Okay, but in any case, if both of these criteria have been met, then it converges. The alternating series converge. Now, I want to be very clear about something. I said very clearly the summation of -1 to the n, or n plus 1, or n minus 1, that doesn't matter, times a sub n. And I said that these values are positive. The a sub n's are positive. So then why do I say the signs are alternating? Because I'm multiplying it. I'm multiplying the positive values, a sub n's, sometimes by positive and then sometimes by negative. In fact, first positive, then negative, then positive, then negative, or it could have been negative and then positive, negative and then positive. That's what's making it alternate. So, if a sub n is greater than 0, okay, provided those two conditions have been met. Provided that condition 1, I just want to write the word and, condition 1 and condition 2, that the limit goes to 0, have been met. So we're going to do some problems accordingly, and move on. So suppose we want to know if the summation as n goes from 1 to infinity of -1 to n plus 1 divided by n, if this converges. Now, I don't think I mentioned this, but the summation of 1 over n is famous. It is called, this is called the harmonic series. Called the harmonic series, and it diverges. It diverges. Okay, this here is going to be the alternating harmonic series. Because we know the denominators are going to be 1, and then 2, and then n will be 3, then n will be 4, etc. But when n is 1, 1 plus 1 is 2, -1 to the 2 is plus 1. And then it's going to change. Actually, they're all going to be 1 or -1. And the signs are going to alternate. -1 to the n plus 1 or -1 to the n, those are going to cause the signs to alternate. This happens to converge, and we're actually going to prove that right now. Okay, this is called the alternating harmonic series. Just to emphasize, if you separate the alternating part, then you will be multiplying by 1 over n. I'm not sure what happened. Let me try to erase this again. So now we're just going to solve some problems. If you separate the -1 to the n plus 1, you're multiplying that by 1 over n. I can always multiply by 1. I get 1 over n after I pull out that alternating piece. Okay, so this here is a sub n, because it's in the form of -1 to the n or n plus 1 times a sub n. That's a sub n. Now, criteria 1 says that a sub n plus 1 must be less than a sub n. Well, a sub n plus 1, is it less than or equal to a sub n? Well, like I said, a sub n is 1 over n. A sub n plus 1 is 1 over n plus 1. Now, since n is positive, n starts at 1. The numerators are equal. Here, I'm just dividing by n. Here, I'm dividing by n plus 1. Imagine you're hungry. There's a pizza pie sitting on the table. You look around and you see a certain number of people, 10 of them, and you're really hungry. If one more person comes, you're less happy, because you're going to get 1 over n plus 1 of that pie now. It's going to be shared equally. You're getting less. Okay, so whenever something is less than something else, you can say it's less than or equal. So that has been satisfied. Condition 1 has been met. Condition 2 says that the limit has to be 0 of a sub n. Well, the limit as n goes to infinity of a sub n, why, that's the limit as n goes to infinity of 1 over n. And 1 divided by more and more and more. Why more? Because n is going to infinity. That's 0. So condition 2 has been met. Therefore, this given sequence, it converges. The alternating harmonic series, I meant to say series, this alternating harmonic series converges. Because they met both of their conditions. The terms were getting smaller, and they were even approaching 0. You don't have, just because you're getting smaller and smaller and smaller, doesn't mean that you're getting closer to 0. I mean, let's suppose you had some a sub n where that was true. The terms really were getting closer and closer to 0. Well, just to take another term and let it equal another sequence, let it equal their a sub n plus 1 more. So the terms start getting closer to 0. Well, if you add 1, they're going to all be 1 higher. Now they're getting closer and closer to 1. Now they're getting closer and closer to 1. Here is 1. They're getting closer and closer and closer to 1. And it's decreasing. It's always going down. It never went up. It's going down as I go to the right. But nonetheless, it's not getting closer and closer to 0. They're getting closer and closer to 1. So let's look at another one. Suppose you have negative 1 to the n over n factorial. Summation as n goes from 1 to infinity. I can say from 10 to infinity. Okay, so realize whether you write this down or not, this is the summation of negative 1 to the n times 1 over n factorial. This here, that's a sub n. The question is the next term, and the a sub n's are always positive. This is positive. That was the initial statement. If you have the summation of negative 1 to some power that makes it alternate times an, and an is positive, then it converges under the following conditions. Really, in the last problem, I should have pointed out that the a sub n's are positive. A sub n, which equals 1 over n factorial, is positive. Now, when you compare these two consecutive terms, is the latter one smaller than the prior one? Is 1 over n plus 1 factorial less than or equal to 1 over n factorial? Well, n plus 1 factorial is n plus 1 times that. N times n minus 1 times n minus 2 times n minus 3. It's n plus 1 times n factorial. Is that less than or equal to 1 over n factorial? Sure. Because I'm multiplying, the numerators are the same, the denominators are the same with respect to n factorial, which is a positive amount, and I'm multiplying it by n plus 1. It's more than 1. That's going to make this number bigger. I'm dividing 1 more over it by more on the left than I am from the right. So you better believe that's true. A sub n plus 1 is less than a sub n. Okay, now are the terms going to 0? So limit as n goes to infinity of 1 over n factorial is that 0. Well, one way of thinking of n factorial is 1 times 2 times 3 times 4 all the way up to the number in front of n times n itself. Well, if this number is getting larger and larger, if n is getting larger and larger, that thing is taking off. Okay, this thing is taking off, and yes, this is going to 0. 1 times 2 times 3 times 4, etc. times n, and n is getting really big. It's infinity. I mean, just the last number itself is going to infinity. And I'm multiplying it by 1 less and 2 less. I mean, 1 times 2 times 3 all the way up to n. It's bigger than n. And if n goes to infinity, well, you better believe this is going to infinity. And if the bottom is going to infinity and the numerator is just 1, it's going to 0. So the second criteria has been met. That limit is 0. So that goes to 0. Excuse me. That series converges. The summation of -1 to the n over n factorial converges. The nice thing about the alternating series test is we don't even deal with the -1 to the you don't even deal with the alternating series. The fact that they alternate. Suppose you have the sine of 2n minus 1 pi. Let me write that over 2. 2n minus 1 times pi over 2. This whole method is the angle. And you have this summation as n goes from, I guess, 1 to infinity. 1 to infinity. Now, you have every reason to assume, like, what are you talking about? Why is this even here? Because it's not alternating. Well, is it? Let's see. When n is 1, see, what happens to 2n minus 1? If n is 1, it's 2 times 1, which is 2, minus 1 is 1. And when n is 2, is 2 times 2 is 4, minus 1, it's 3. And when n is 3, you get twice 3, which is 6, minus 1 is 5. And when n is 4, you double n, you get 8. 2 times n is 8 if n is 4. Minus 1 is 7. You get 1, 3, 5, 7. Okay. So let's look at that. What you get is the sine of, so this part is 1, 3, 5, 7. So you get 1 pi over 2. The pi over 2 doesn't change. Plus the sine of 3 pi over 2 plus the sine of 5 pi over 2 plus the sine of 7 pi over 2, etc. The number of pi's over 2's. The number of pi over 2's, the number of pi over 2 is 1, and 3, and 5, and 7. Well, let's look at the sine graph. Let's look at the sine graph. Let's look at a couple of sine waves. Here is 2 pi. Here is pi. Right there is pi over 2. 1 pi over 2. Here is 2 pi over 2. Over here is 3 pi over 2. Right here is 4 pi over 2, which is 2 pi. And then over here is 5 pi over 2. Over here you have 6 pi over 2, which is 3 pi. 7 pi over 2, 8 pi over 2, which is 4 pi. Well, you get 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Pi over 2 is 1. The next one, 3 pi over 2, is negative 1. And then it's positive 1. And then at 7 pi over 2, it's negative 1. Signs are alternating. This is just the summation of negative 1 to the, well, if we want to start n with 1 to infinity, the first one we said was 1. This sine of 1 pi over 2 was 1. So if I use n, and n is 1, the power will be odd. Negative 1 to the 1 is negative 1. So I add 1. Now it's even the power. Okay. So then what's a sub n? Well, you need to be mathematically mature enough to realize that whenever you want, whenever you need to, you can multiply by 1. That's the a sub n. A sub n is just 1. Now, first of all, if you think about it for a moment, and we talked about this problem before, if you have 1 minus 1 plus 1 minus 1 plus 1 minus 1, well, actually, I think what we talked about was whether or not the sequence converges. Do the numbers 1, negative 1, 1, negative 1, do they approach any given number? And the answer was no. That doesn't mean the sequence won't do that. Well, at least in theory. But in reality, it's not going to work. Here, up to here, the sum is 1. You add 2 of them, it's 0. You add another one, 1. You add another one, 0. Plus 1 is 1. Minus 1 is 0. Plus 1 is 1. Minus 1 is 0. The sum is not approaching any one number. It's alternating, oscillating between two numbers, 1 and 0. 1, 0. 1, 0. It's not going to add up to anything in the end. And if you apply the alternating series test, it will show that. It is true that a sub n plus 1 is less than or equal to a sub n. Oh, actually, that's not always true. I was thinking they were going to be, that they're all 1. They're all 1. So yes, 1 is less than or equal to 1. That's a sub n. All the a sub n's are just 1. So criteria 1 has been met. This symbol is true. This symbol was valid. But the second one's going to fail. The limit, as n gets bigger and bigger, of a sub n, well, a sub n, I'm going to take the limit of it, a sub n is 1. As n gets bigger and bigger and bigger and bigger, good old 1 stays 1. It's not 0. Therefore, it diverges. It failed the test. For this to converge using an alternating series test, well, first of all, it has to alternate. And we did show that it alternated. And I kind of forgot to show what I'll call step 0. Since AN's equal 1, that implies the AN's are all bigger than 0. Bigger than or equal to 0. So that criteria has been met. Condition 1 has been met. Condition 2 failed. Don't even bother using this test until you realize it's alternating. It's alternating. And just because it's alternating, just because you have a negative 1 to the n plus 1 isn't enough to say it's alternating. And let me show you that very clearly. If you have negative 1 to the n, well, if n goes 1, 2, 3, 4, 5, those signs will alternate. Negative 1 plus 1, negative 1 plus 1. But you know what? If you multiply it by another negative 1 to the n, that's negative 1 to the 2n. 2 times an integer is always even. This is just 1. This is just 1. That is the summation of -1 to the n times -1 to the n is the summation of 1. It's not alternating. That is why they say very clearly it has to be alternating, and the rest of the stuff must be always positive. This wasn't always positive. In fact, when this was positive, so was this one, so the product was positive. When this was negative, this being the same, it too was negative, and the product was positive. It's always positive 1. So be careful. You could find the -1 to the n, but what's left over better be positive. In some, you might be realizing, no it doesn't, this guy's completely wrong. Well, yeah, if it's always negative, I can factor out the negative sign. If you know, for example, the summation of -1 to the n over n converges. Let's just say to 7.2. That's not true, but let's suppose that for a moment. That is the summation of -1 to the n of 1 over n. This is 7.2, and then goes from 1 to infinity. Well, if you have the summation of this, well, just factor out the minus sign. So you have -1 to the n of 1 over n with a minus sign in front. Well, I'm claiming that that's 7.2. Well, 7.2 with a minus in front. It will also converge. So I'm not sure why all textbooks, that's why I wrote it that way. All textbooks say that a sub n's have to be positive. That's nonsense. I just didn't want to deviate from your book. Every book says that. Okay. That really finishes the material on testing alternating series. There's something, okay, let me do that in the next tape. For remaining theorem.